This is lecture on chapter 4.3, Derivatives and Shapes of Graphs for Calculus 1. And no crazy wigs today, so we're not going to be looking at any historical figures in math. Most of today will be some review, and then specifically how derivatives relate to graphs, and we've already covered a lot of this. And then we're going to learn some new things about the second derivative. Now, for me anyway, when it comes to derivatives and graphs, I tend to be very visual, and I've used a lot of visualizations in my lectures. But when we get to slopes and then the derivatives, which is a slope as well at a point, it starts getting a little, I don't know if counterintuitive is the right word, but I really have to slow down and think about what's happening with the graph. And then because we might be graphing a derivative, so we're graphing the slope, and if we're doing the second derivative, we're graphing the slope of the slope. So it can be a little bit confusing. So take your time with this lecture, and take your time when you're solving these problems. So remember that we already said that since the derivative is the slope at any point, if the derivative is greater than 0, then the slope is positive, and a positive slope means the function is going up. So our revenues are increasing or something's positive. If the derivative is less than 0, this means the derivative is negative. Since the derivative is the slope, this means the slope is negative, which means our function is going down. Okay, pretty straightforward. So looking at this example, between what 2 points is the derivative positive, and between what 2 points is the derivative negative? See if you can answer that. Hit pause for just a second. So remember, the derivative is positive when our function is going up. So between a and b, our function is going up. But look, later on, it's also going up between c and d. So the function is positive both between a and b and between c and d. Between b and c, the function is going down, so our derivative would be negative. Okay. Again, this should be review, and that should be a pretty simple problem for you to see and visualize. Okay. We've already touched on this before as well. This is the example that I gave with the mountains and the valleys. And we said if the derivative goes from positive to negative, then we have a local maximum. If it goes from positive going up to negative going down, then we have a local maximum. If the derivative goes from negative going down to positive going up, we have a valley or a local minimum, and that's all this says here. We also learned a special case of a horizontal point of inflection, and this is where the derivative doesn't change polarities. It goes up, it hits 0, and then it goes up again. Or it goes down, hits 0, and goes down again. And this I referred to as a cliff on the mountain, right? It wasn't the mountain peak, it wasn't the valley, it's just a cliff. And this is when the polarity, again, doesn't change before and after the 0. So it's positive, 0, positive, or negative, 0, negative. Again, none of these, and these are not maximums or minimums, these are horizontal points of inflection. None of this is new yet. Okay? So we have a new idea here called concavity. And concavity simply refers to the direction of a curve. That should say curve, not the cure. So a concavity, we have concavity up or concave up when the C, and you see like there's a C here, like a laying on its back, points up. This is like a spoon. A spoon is concave up. Well, if you're trying to use it, you should be using it concave up. Concave down, and you have milk in your lap or coffee in your lap, whatever. Okay. Notice that the function, the curve, is always above the tangent line. The function, all of our tangent lines are drawn below the curve. So when we have a concave up curve, the tangent lines are below the function, or the function is above them. Concave down is when the C points down. Again, your spoon is upside down. Think of a spoon. Concave up, this is the way you use it. Eat them up. Concave down, and your milk from your cereal or your cereal's in your lap. And notice here that all the tangent lines, they're hard to see there, but you can see them always occur above the curve. Okay? It's getting a little complicated now. All right. So this is where I get, like I say, sometimes this gets confusing because what looks like's happening here throws my brain off, my intuitiveness off. Okay. So notice for curves that are concave up, the slopes are always increasing. Okay. Now, like when I look at this, I go, wait, but where am I? There we go. This is going down and this is going up. So how can it always be increasing? The slope is always increasing. So remember that when a function is going down, the slope is negative. And then it's getting closer and closer to 0, and then it's getting positive. So the slope is negative, and then 0, and then positive, just like a number line. Negative, then 0, then positive. So the slope of a concave up curve is always increasing, moving from negative to positive. And so although my intuitiveness here, when I look at this, say, wait, it's going down, then going up, I'm thinking of going down as being not increasing. But remember, we're talking about the slope. When the function is going down, the slope is negative. So our values of the slope go from negative to 0 at the minimum here, and then go up to positive. So it's always increasing. Okay? So the derivative, f prime, is always increasing. Our first derivative is always increasing. Now remember, this is where it gets even more complicated. If a function is increasing, this means its slope is positive. Okay? If a function is increasing, its slope is positive. So if we have a concave up curve, the derivative is always increasing. That means the slope of the derivative. Now remember, the derivative, the first derivative is the slope of the function. What I'm now talking about is the slope of the derivative, the slope of the derivative. And since we know the derivative is always increasing, then its slope has to always be positive. And remember, the derivative is the slope, so we're talking about the derivative of the derivative. Okay, I'm not going to say that again. You might want to rewind that and hear that again. So for a concave up curve, the slope of the second derivative is positive. Okay, so if our second derivative is positive over an interval, then that function is concave up. Okay, so I built that up there, and I'm going to kind of do it again here so you can hear that same thing again in the other direction. So notice now, if we have a concave down curve, by that same logic, the slope is going up, so it's always positive, 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 but it's getting smaller and smaller, getting closer to 0, and then it starts going down, which means the slope is now negative. Positive slope, getting closer to 0, now negative slope and getting steeper down. So notice our slope here going from positive to 0 to negative, positive to 0 to negative, positive to 0 to negative is always decreasing. All right? So this means that the first derivative is always decreasing. The first derivative, the slope, is always decreasing. And if a function is always decreasing, the derivatives, if the function of the derivative is always decreasing, that means its slope is negative. So the second derivative is negative over that interval. Then we have a concave down curve. Okay? I know that's a lot to take in. You might want to listen to this one slide again. Because for me even, I have to slow down and really think through these. Okay? All right. So let's see what's happening here. Notice the sine function to the right. We're going to go to another idea here. This function moves back and forth between concave down and concave up. Concave down and concave up. So it's moving back and forth between the concavities. Down, up, right? Concave down, the spoon is upside down. Concave up, the spoon is right side up. concave down, the spoon is upside down, concave up, the spoon is right side up. Okay. Now there's a point, because it's going from concave up to concave down, there's a point on here where it has to switch back and forth. Now the sine curve is a nice one to see that, because all the x-intercepts are that point on the curve where it goes from concave up to concave down, or vice versa. This is called a point of inflection. Okay, so in this graph here, the point of inflection are all the x-intercepts. So it has one here, 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 and if we continued on. Now remember what's happening here with concave down. With concave down, the slope is always decreasing, so the second derivative is negative. With concave up, the slope is always increasing, going from negative to positive. So the second derivative is always positive. So when we think about in terms of the second derivative, we're going negative to positive. So again, because it's a continuous, it has to hit 0 in the middle. And that spot, that point of inflection, is when the second derivative equals 0. Okay? So when the second derivative equals 0, we have a point of inflection. And this is when we move from one concave to the other, up to down, or down to up. Okay, so that's the point where it's changing. So if we're trying to find the point of inflection, we find the second derivative and set it equal to 0. Okay, so now we're going to try to do a problem here. We're going to find the points of inflection, which we just found out. We set the second derivative equal to 0. And find the concavity of the graph. So we're also going to have to, if we find those points of inflection, we can find out what's happening before and after those points of inflection to see if it's concave up or down. And those are our breaks. Okay. So first we want to find the second derivative. Well, in order to find the second derivative, we have to find the first derivative. Again, pretty simple derivative there, and even simpler there. Okay. Now we want to find the points of inflection by setting the second derivative equal to 0. Okay? Well, if we factor this and we factor out a 6x, we get 6x times x minus 1, set each of those equal to 0, and we get x equals 0 or x equals 1. Okay? So these are our points of inflection. This is when the function is turning from concave up to concave down. Okay? Now it asks for the points of inflection, okay? So we found the x values, but these are not points, these are x values. A point is an x and a y value. So we have to find the y values by plugging these back into the original function, So our 2 points of inflection, and I don't think I've written them here, I haven't, are 0, 5, right? A point, 0, 5 in parentheses, and 1, 9/2. The x value, the y value, the x value, the y value, okay? Points of inflection are about the original graph function, here, okay? Now we want to find the concavity of the graph. Now the easiest thing to do here, let me see if I have that, is to think of this as a number line, and we have 2 points, x is 0 and x is 1, that's why it's here. We want to figure out what's happening on each side of this number line, right? We want to find out the concavity before and after. Now remember, the second derivative gives us concavity. So the easiest thing in my mind to do is to put this in your calculator as a function, 6x squared minus 6x, put the second derivative in there, and then again look at your table or your graph function, and underneath that is a table, and then just look at the table. What's happening when x is less than 0? Are these values for the second derivative positive or negative? What's happening on values between 0 and 1? Now here you might have to change your table function because most tables are set at integers of 1. Well, you can change the table. It's one of the buttons across the top. I think it says table set. And change your interval to a half. So look at a value here, and is it positive or negative? And then look at values greater than 1, and is the second derivative positive or negative? So if we do that, we find out that values less than 0, the second derivative is positive. Between 0 and 1, the second derivative is negative. And between 1 and greater than 1, it's positive again. So remember, a positive second derivative is concave up. A negative second derivative is concave down. Where's my mouse? There we go. And again, a positive is concave up. So our graph is going to go from up, concave up. Remember, the spoon is right side up, to concave down. The spoon is upside down, to concave up. The spoon is right side up again. And here you can see the graph. Now, these aren't very intuitive to see where it goes from concave up to concave down. And this I like this graph because it isn't so easy to see like the sine wave was. So here we can see it's kind of concave up. And then for just this little part, it's concave down. And then it goes back to concave up again. Okay. So again, just a little review here. If the second derivative is positive, we have concave up. If the second derivative is negative, we have concave down. Now what we can do here is we can use this to figure out, if we figure out that we have a maximum or minimum, if we do the second derivative and it's positive, then we have a minimum, right? So now we have a way to figure out if, without looking before and after the local max or minimum, to figure out, is it a max or minimum? All we have to do is do the second derivative and see if it's positive or negative. Again, if the second derivative is positive, we're going to have a local minimum. If the second derivative is negative, because we're going to have a concave down, then the local max or minimum is a maximum. Okay? So the second derivative test says you find the first derivative and set it equal to 0. Again, these are giving us our critical values, where we have a max or a minimum. Then we plug the x value into the second derivative. So we need to find the second derivative and then plug whatever x value here we find, the critical values, and see if it's positive or negative. Again, if it's positive, then we have a minimum, right? Because we have concave up, we have a valley. And if it's less than 0, then we have a maximum.